Hi, good evening. Hello, hi, good evening. Thank you for joining. So I'm just waiting for a few more people to join to begin this session. So, Mr. Jainendra, so your name is
Yes,
Jainendra,
sir.
right? Yes. Yes. Uh, so, so did you join the previous session?
No, sir. This is my first
First session.
lecture session, and I
Okay.
have not written any classes,
Sorry, I
SPAM
didn't hear.
classes.
Okay, okay,
So this is my first session, and I also did not do any of classes of modeling and simulation till now.
okay.
Completely new.
I actually didn't hear you clearly. So, so you were not able to attend previous session. That's what you were saying, right? So did you were you able to actually uh, get access to the previous sessions recordings and slides? Were you able to get access to that?
Yes, sir, I can get access.
You were able to access it. Okay. 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 I think maybe we can wait for just 1 minute more and then we can just start with the session. Otherwise.
Yes, sir.
Yeah. So, Jainendra, thank you for joining this session. So basically, just wanted to get to know about you. So which place are you joining, and like, what is your background? So, can you just tell me quickly about that?
Sir, I am from Lucknow, and I am doing mechanical engineering. I am now at second year.
Okay. So you're
My
from
college,
Lucknow, you said, right?
yes, sir. And my college name is Khwaja Muhyiddin Chishti Language University. It's a government university.
Okay. 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 So you are doing mechanical engineering.
Yes, sir.
Mechanical engineering, right? Okay.
I am doing this course for job purpose in research and development and production engineer.
So Jainendra, actually your voice is not clear. So
Doing course for job purpose, research and development engineer, formula of research and development engineer and production engineer.
I'm actually sorry. I'm not really able to hear you clearly. So is there any way you can like have a better internet connection? Like I don't know. Like, I'm not able to hear you clearly.
So now here
No, no.
I'm trying to join by mobile.
Sorry.
Sir, can you hear me now?
Now it is better. Yes, yes.
Okay, sir.
Yeah, this is better now. So no, I was just asking you. You are doing your mechanical engineering right now.
Yes, sir. Yes, sir.
Okay. Okay, sir. So I think we can just start with our session.
Yes, sir.
I think we will not wait for anyone else more to join.
About yourself.
So are you able to hear me clearly?
Yes, well, clearly.
Okay. Okay. Fine. So I'm presenting. So can you see my screen?
No, sir.
So are you able to see my screen? I'm sharing my screen.
Now I see that your
Sorry.
uh, now your screen disappeared. Now visible.
Is it visible now?
Yes, sir. Now visible.
Okay. Yeah. Fine. So so basically, let us basically I'll just first start with my own introduction.
Yes,
So my name is Parth Joshi.
yes,
So I'm basically doing my PhD at IIT Bombay,
yes,
and so basically as a part of my PhD program, so I got this Prime Minister's Research Fellowship for my PhD, and so as
yes,
a part of that, so I'm basically getting this opportunity to interact with you as a part of this course to conduct these weekly tutorial sessions. So So I have been doing these kind of sessions since 2020 two. So I think so I started in 2022. So now I have been doing this for like 2 3 years for different
yes,
courses. So this is like one of I think my second time I'm doing this course. So so basically what is my general plan for these sessions is that like I'll just try to give you some overview of the content covered in that week. And
yes,
then, so I have like some sample problems which I picked up, which are related to the course content for this week. And so we'll basically try to solve them in this session. Also, if you have any doubts from your side, any questions like related to the course content or anything, so you can also ask those uh, in this session. So I'll try to answer those questions like if possible, and so as far as I can, I'll try to answer them. If I'm not able to answer, so you can like maybe So I'll actually try to answer it in then maybe the next session. Or if after the session, if you have any doubts, so you can. So I have my email, which is shown over here. So in the like slide. So you are able to see the slide, right?
Yes, sir, I can see
Yeah,
the
yeah. So
side
I have
slide.
my email written over here. So you can email me your questions if you have like later on. So
Sir.
so like that. Yeah. So before we start, so like, do you have any questions or any doubts from your side, like related to the course, like previous weeks or this week content? Anything?
No, sir, I don't see the course now. Briefly,
So I still cannot hear you clearly.
I have no.
So sorry, I'm not really able to hear you clearly. So is there any way you can improve your audio, like audio thing? Like, so are you joining from your phone or something? So like, I don't know, the network is not that good probably.
Now, okay.
Yeah, little bit. Yeah, so what were you
Uh,
saying?
sir, I have doubt.
You don't have any
Because
doubt.
yes, sir, I have not done yet.
Okay, okay, fine. Fine. So maybe we can start with whatever like the presentation, and then later on, like if in the meanwhile, if you have any questions, like you can ask me like at any point of time. So yeah, so so there is one more person who has joined. So yeah, welcome Shyam. Shyam, right? So just so there is a person named Shyam Kumar who has joined. So can you just like unmute yourself and just speak? Um, okay, anyway, fine. Basically, welcome to this session. So like this is our second session, and so we are now starting with the discussion of the content related to this course. So so the first, basically this week's content is mostly related to bond graph modeling. So the concept of bond graph modeling has been explained in this week's lectures, and the basically the elements which are used in creating a bond graph, those have been covered, like and then also like the concept of causality, which is used basically while we, so it's important to assign a causality to a bond. So the basic concept of the concept of power transfer between different, like so this concept of bond graph is applicable to any multi-domain systems where energy is transformed from one form to another. So it's applicable to any systems which are like involve conversion from, like mechanical, electrical, hydraulic, or any kind of these systems. So this advantage of this concept is that we it gives us a unified approach to system modeling. So so any kind of system, so it can be like mechanical, electrical, hydraulic, or any kind of system. So we can use this approach to create a system model representation using the bond graph approach, using the same elements basically. So we can like let us say for a mechanical system, whatever is a mass. So in an electrical system, it's analogous is let us say inductance. So So like that, so there are several elements which turn out to be analogous for different classes of systems, and then we can use this uh, to our advantage is that we can have a common representation in terms of a bond graph for different kinds of components and use the same bond graph elements to model different kinds of systems. Then the concept of generation of system equations from the bond graph has been described, and then the like methods of drawing bond graphs for electrical and mechanical systems have also been discussed. So before we start, so I just wanted to know whether so all of you are whether you are clear with the basic elements that we have in the bond graph. So can someone of you tell me which are the different elements that are like we have in the bond graph? So the fundamental building blocks that we have. So which are the elements that we generally use?
The electrical element,
Yeah, sorry.
electrical elements,
Yeah, so like you have basically different types of elements like one is called as the basic like inductance like or inertia.
resistance.
Yeah, resistance is there, then capacitance model is there, like so those kind of elements. So those are the three, like inertia element, which can represent either a mass or it can represent an inductance. Then we have the capacitance element, which can represent either a capacitor or a spring. Then we have the resistance element, which can represent an electrical resistance, or it can represent, let us say, a hydraulic resistance, which is created because of orifice, or we can use this same element to also describe, let us say, viscous drag or like, damping in a mechanical system. So these are the three basic elements. Apart from that, we have the other elements which are called as transformer and gyrator. So those are also other two elements. So which basically, so the transformer is basically having like it's kind of converting, basically giving a relation between flow variables or the effort. So and the gyrator is, so basically transformer can represent like either gears, a set of gears, or it can represent like the electrical transformer where voltage, let us say, so voltage is amplified and current is reduced by the same factor. So like in a step up transformer, voltage is amplified, like voltage is like increased by a certain factor and the current is reduced, so the power remains the same. So the power transmitted is the same, only the relation between the like the effort and flow, that so it just changes by a certain factor. So similarly, in case of gears, like let us say if we have like a set of gears, so then we can either increase the torque and reduce the speed, or increase the speed and reduce the torque proportionately. So that is basically what the role of transformer is. Then the other element is called as gyrator, which is basically like a which is somewhat like, so it can describe an like component like electric motor or generator, where basically mechanical energy is converted into electrical, or electrical energy is converted into mechanical energy. So so in that case, it's basically the effort variable is converted into flow, or flow is converted into effort variable. So that's the implication, like in terms of the bond graph as such. Then we have the source of effort, like source effort and the source flow components also. So which basically represent, like let us say if we have a voltage source, so that's the source of effort. Or if we have a current source, so then that's generally called as a source flow. Those are some of the basic elements that you use in the bond graph. And apart from that, we also have junctions in the like bond graphs. So one type of junction is called as zero junction. The other type of junction is called as one junction. So in zero junction, basically we have like the effort is equal for every bond, and the net sum of the flows which are coming towards, let us say, the junction. So the sum of those flows would be zero. Whereas in case of one junction, it represents the equal flow basically condition, and also uh, it means that in case of a one junction, the effort variable, so the algebraic sum of the effort variable in the junction is basically zero. So that's the general idea of the components. Now, based on the direction of like on which side of the bond we are calculating the flow, or so basically depending on the direction of on in which basically the effort or flow is applied, so we generally assign the causality. So there is a general rule of uh, how in which we, or basically the general rule in which we assign the causality. So those have been described. So first of all, we assign the causality to the sources. Then we basically assign the causality to the transformer and gyrator components, and the zero junction and one junctions. So those are the components which have the fixed causality. And in case of the capacitor and inductor, we have the desired causality, which is based on the integration based representation. And so lastly, we assign the causality to the resistance element based on whatever causality, after consideration of causality of all the other components, we assign the causality, because resistance has a free causality, so it can have like the causality being assigned on either side. And in case of the causality of junctions, so in case of the junction, so like zero junction, so where we have the common effort, so for that junction we have only one equation which describes the relation between the flows. So there is only one causality bar in case of a one junction, at a one junction. Whereas in case of the one junction, so we have only one equation which relates the effort. So therefore, we need to have, like, let us say if n bonds are coming towards or like which are related to, in case of the the n number of bonds are involved in that, let us say, particular junction, let us say one junction. So then in case of one junction only, uh, there is a one effort equation, so therefore we have to have n minus 1 causality bars at the one junction. So so those are some simple rules which help us while assigning the causality in the bond graph. And there are also some rules for assigning the causality for the uh, the transformer and gyrator elements. So based on these rules, we basically follow this systematic approach and try to create the bond graph for any system as such. So now let us come to this uh, flow chart. So let us basically try to understand what is the difference between the usual modeling like approach, uh, where we use differential equations, and compare it with the bond graph approach. So in both cases, we start with a physical system and then derive a engineering model for that. And then from the engineering model, so we basically try to draw a bond graph. So in case of the bond graph modeling approach, we based on the physical, let us say engineering model, like physical engineering model of the physical system, we try to draw a bond graph of that. So it's like a graphical representation of that, and we also like take into consideration all the factors of causality and all those things, and then create a bond graph. In the usual approach, we generally try to apply some of the physical laws like Newton's second law and all, and try to derive the governing differential equations for the engineering model, and then use like techniques like block diagrams, and then basically provide it in a format where the computer can understand. So either we can write a code, like a, let us say in MATLAB, we can either write a code to solve the differential equation, or we can alternatively we can also draw block diagrams. For example, Simulink is like a tool which uses the block diagram kind of representation. So we can build the block diagram model in Simulink, and then uh, basically provide basically the inputs in the format where in which the computer can understand, and then basically use the simulation tools like MATLAB, Simulink, or any other tool to get the output. Now, in case of bond graphs, we can basically utilize the fact that we have this unified representation and the common set of elements for any kind of system. And once we have the bond graph, so we can actually automate the process of creation of the equations, or like the equations of motion or differential equations. So like like let us say there are some softwares which have been created which use this bond graph kind of modeling approach. So then the differential equations in state space form or whatever form, so they are basically getting created inside the computer itself. So this process can be automated, and then the software can, like, we will just provide the inputs, like for how much time we need to simulate the system and just the basic model parameters, and then we can use the simulation software to get the output. So this is like you can say in some sense the advantage of using these kind of this kind of approach using bond graphs. So we can basically automate the process of creation of the differential equations using this approach. So that's the main advantage of this bond graph approach. So any questions till now?
No.
Okay. So there are some simulation softwares like which, for example, there is a software called as 20 sim, which uses this bond graph kind of modeling approach. So this software you can try it, like so you can also explore this software on your own. It's not a free software, but I think you can use a trial version at least to get some idea of how to use these bond graph kind of approaches to model a dynamic system. In addition to that, you can also use this in MATLAB. So there is a tool called Simulink. So and within Simulink, so there is also another library which is separate, which is called a Simscape, and in which basically is like a physical modeling kind of a tool. So like Simulink generally uses block diagrams to create the system model, whereas in case of Simscape, we use the physical modeling kind of an approach, which is like similar to the way we create bond graph representation. So it also has a bond graph modeling library, so it is compatible with that bond graph kind of modeling approach. There are also other commercial tools available in the market. So like these are one of the, I think, well known ones. So you can also try it out. You can explore these tools on your own. So if time permits later on in the course, I think I'll also try to see whether we can, I'll try to show you a demo of at least one of these tools, how we can use these tools and for modeling, and especially highlight the bond graph modeling kind of approach part of that. So yeah. So in the previous session, so I actually gave a demo on how to use MATLAB for create like for simulations, like so how to use some of the features in MATLAB to write programs and then run the model and create plots to visualize the system behavior. So like I'll try to show you some demos like as and when, like in the appropriate times in the course. And yeah, so that's that I think hopefully it should help you. And so all these tools are generally used in industry also for system modeling, where we do simulation studies to understand the behavior of different systems, and it actually helps us save our time during the design, like designing any product. So we generally build the system model in a virtual environment and subject it to the different operating conditions, and try to use these simulation tools to see how the system will perform in realistic scenarios. And so we basically try to design the system for all kinds of scenarios before even the product is actually built. And then after that we do some testing to validate whether our product is actually performing in as expected. So yeah, so this I wanted to give you some context, so that so as to motivate you and try to understand, make you understand, like what is the importance of all these modeling and simulation kind of tools. Okay. So so any questions or comments till now?
Uh, yes, I want to demo in Simulink because I was and I am unable to do Simulink tool.
I am not able to hear you clearly again. Sorry. What were you saying?
I want I want to demo because last time I tried to use Simulink tool, I am unable to do it. I can't find it.
Okay, you tried to use Simulink.
Yes, sir.
Okay. Yeah, I'll try to show you some demo. Like, so any specific application like you that you are trying to use in Simulink, like any particular, like, can you tell me like what exactly were you trying to do in Simulink?
Sir, I am trying to do free mass, which is dropping down free fall and key mass.
You are trying to model a spring mass
I
system.
do, sir.
So you are trying to use the spring mass system, right? Hello? Yeah, so you are basically trying to use the Simulink for creating a model of the spring mass system, right? Yeah, so I'll actually try to show you a demo on that. Right now, I have not actually planned for that, but yeah, so I think, yeah, maybe in the next session or so, I think maybe I'll try to give you that. So I'll prepare the demo and show it to you at that time, so it will be like helpful for you also. Does that is that okay? Yeah. Yeah, so now we can just start with some of these simple problems, uh, and try to answer them. So the first question, is so basically these are some sample problems which I have picked up, which will be like similar to the questions that you will be answering in your assignments. So some of them are multiple choice, some of them are like we have to derive the answer, like do some derivation to get the answer. So we'll try to solve some of these problems as we go along. And yeah, so if you have any doubts, like you can also ask me right now. So in this question, we can see that there is a bond graph drawn over here, and we have been given that there are like two forces F1 and F2 which have been applied. So 2 newtons and 3 Newton forces. So here we have to find out what will be the effort entering the zero junction. So here we have like in the bond graph, so we have a source effort component SE, and so F1 and F2, and the force is being applied, and so there is a one junction. So basically it's like, let us say we can visualize it as a mass on which like these two forces are applied, and then what will be the combined effort that would be applied at the zero junction.
5 Newton.
5 Newton, right? So basically the effort at 3 so is sum of the efforts like F1 and F2, so which is 2 plus 3, which is 5 Newton. So you're right. So now which is a strong bond which is as given in the figure
1.
1.
Yes, sir.
Okay, so why do you think 1 is the answer?
Because one is entering a direction and other are all going elsewhere.
Okay. So I think as per what is explained in the slides, so let us just check once in the slides. So are you able to see the slides? So here, as per the slides, so this is the the bond which is going away, like which has the causality away from the one junction. So this is the strong bond. So in this case, we have basically the it's a one junction, so which is a common flow junction. So we have the flow at basically flow at along the bonds 1, 2, 3, and 4 all are equal, and the effort is basically, so we have one uh, relation which gives the relation between the effort and the so the other relations basically, so F4 will be equal to F1, F2 is equal to F1, F3 is also equal to F1. So these are all strong relations. So the bond number 4 should be actually, I think, be the strong bond here. So do you agree?
Yes, sir.
So now the next question is like which of these things are correct with respect to bond graphs. So what all of these things are achieved when we use the bond graph approach?
unification and multi-domain approach.
Yeah, it's actually all the three are being achieved here. So unification is definitely being achieved because we can use the common representation for all sorts of systems, and as I mentioned, like multi-domain kind of systems we can model using this approach. And also because of the nature of the bond graph, so as I said, like we can automate the process of creation of the system equations. So that is we can have an algorithm which, like, step by step process which so there is a step by step process of creating the bond graph itself, assigning the causality, and then after once we have finished assigning the causality, then we use basically the fact, like, the uh, effort and force at the we first identify which are the system variables, based on, like, which are the inductance and capacitance components, and then based on that we identify which are the system variables and generate the system equations based on that. So we can basically automate this process, develop some algorithm, and so that the computer can perform these things for us. So all the three things are achieved in case of bond graphs. Now the next question is that we have to match the columns. So on the left hand side we have certain quantities which have been listed. In the second column also we have been certain quantities. So we have to match both of these, depending on what is the you know based on the whether they are from the same category or not. So we have to select based on whether the quantity is an effort quantity or a flow quantity, or it is a transformer modulus or a gyrator kind of a modulus.
Sir, I have no idea.
Okay. So here, so the torque. So here torque is basically like a effort quantity. So in column 2 we have to look for the quantity which is analogous to a effort quantity. So which quantity of the second column is a effort quantity?
I have no idea.
Uh, Sorry, I didn't hear you actually. So I think it is pressure.
Sir,
So yeah,
yes,
so
pressure.
pressure is a basically a quantity which represents like a effort. Then angular velocity is a variable because it's a velocity. So now in second column, the flow variable is current, right? So what we found out is that torque is analogous to pressure. So one column, like first element in column 1 is matching with C. So 1 is matching with C. Then angular velocity is matching with current. So torque is basically matching with pressure. And angular velocity will be matching with current. Then gear ratio. So gear ratio is a transformer kind of a modulus. Now, which one of these on the right hand side like is analogous to a transformer modulus?
A turns ratio of electrical transformer.
Yeah, you're right. So basically, gear ratio is the torque multiplication or speed reduction factor. Similarly, turns ratio will be the the ratio in which the voltage or current will be changing. So that is matching with this. And then the torque constant of the DC motor will be matching with the piezoelectric coefficient. So now in torque constant, what we do is basically we express a relation between the current and the torque. So torque is a effort variable and current is a flow variable. So in case of the piezoelectric coefficient, so we basically give the relation between pressure and the voltage created. So pressure is a effort variable and the current the voltage induced. So the deformation, so there is a relation between the deformation and the voltage generated across the the opposite surfaces. So that is like a transformation of flow variable into effort, so which is like a gyrator. So the correct answer would be, so one is matching with C, then 2 is matching with A, 3 is matching with D, and 4 with B. So this would be the correct answer. So B, option B. So now here we have been given a lever. So where two forces and two velocities have been shown, F1, F2, and x1 dot and x2 dot. Now we have to find out what is the transformer modulus for the given bond graph.
PA.
Option A.
Yes, sir.
Okay. So let us check that. So in case of a transformer component, we have to basically find out what is the relation between the flow variables and or the effort variables. So let us say if m is the modulus of the sorry. So let us say if m is the modulus of the transformer component, so we have to find out that F2, just wait a moment. So are you able to see my screen that I'm presenting?
Yes, sir, I am able to see. Yes, sir.
So are you able to see the PowerPoint slide that I am sharing?
Yes, sir.
You are able to see?
Yes.
Just a moment. There is some problem with my uh, network connection, so I'm just trying to figure that out. So are you able to see the PowerPoint?
Yes, sir. I am able to see.
You're able to see the PowerPoint screen?
Yes, sir. Yes, sir.
Okay. So I'm actually logging in from another device. So no, because the thing is that I have to this has to be also come into the recording also, because if that is not coming in the recording, so then that will be a problem. So uh, so just give me a minute. So sorry. So because there is some, I think the internet connection is a little bit slow. So just let me check whether I can fix this. So now are you able to see whatever I'm doing on the PowerPoint screen?
Yes, able to save.
Yeah, okay. Yeah, this is better. So I think the internet connection was a little bit slow. So yeah, yeah. Anyway, so basically we were looking at this problem. So now this transformer modulus should be M. So we have to find out the relation between the the flow variables and in case of this so so ideally this direction of the velocity, so in the direction in which the lever will turn, so when we turn the right hand side end with this velocity, then it should actually be this way. So the indicated direction is actually opposite, so therefore the transformer modulus will be negative. So either it should be either minus a by b or b by a. Now which one of that will be correct? So the basically how do we find out that? So the angular, so x2 dot is basically the b into some whatever angular velocity that we will get, and x1 dot should here as per whatever is indicated, so it will be minus of a omegas, right? So basically x2 dot by b is equal to minus x1 dot by a. So x1 dot is equal to minus a by b 2 dot. So yeah, so the transformer modulus can be minus a by b. So yeah, so we just derived that the it will be minus a by b. Yeah, which of the following bond graph element takes least preference for causality assignment? So when we assign the causality, which one will be the last preferred element?
I have no idea.
Yeah, so when we assign the causality, we will first um, basically assign the causality first to the source effort. So because it is fixed, then we will have the junctions, like assign the causality to the junctions and then the source effort and the source flow, they have fixed causality. Then these junctions have the fixed causality. Then the transformer and gyrator elements will also have a fixed type of causality depending on which side the flow or effort is being calculated. After that, we have the inductance and capacitance element, which have the preferred causality. So based on the integration based representation. And after that, last priority is given to the resistance element. So the resistance element is the one which has the least priority. So yeah, so basically this,
Makes sense.
so the resistance element will be the one which will have the least preference. So there is still some problem. There is still some problem with my network, so because the I'm not able to see my screen here.
And now visible PPT.
Your
PPT is
PPT is
visible.
visible.
Yes, it is visible.
Okay. Because I am not able to see it here on my screen, so then it will be like, so you will be able to see it, but in the recording it will not appear. So that will be a little bit of a problem. So that's why I'm actually, there is a problem. So later on, because people who will be referring to the recording, they will not be able to get the access. Yeah, now I think it has appeared. Yeah, fine.
Yes, sir.
Yeah, so the next question is like, according to the sequential causality assignment procedure, so we will have to basically assign the causality in this bond graph which is shown over here, assuming that the resistance element is linear. So we have to go one by one. So by each, for each element, like for each bond, we have to assign the causality bar. We have to draw the causality bar for each bond. So now we will use the rules that I just mentioned in the sequential causality assignment procedure. So first we have to assign the causality for the source source first. So the source, which are the sources here? So there is a source effort. So the component which is called SE. So that is the source effort. And so for the source effort, the causality is actually fixed. So So in case of the source effort, where would be assigned the causality? So because the force flow is computed on the this other side, so therefore we assign the causality on the other side for source effort. So are you able to see whatever I'm drawing? So on this in the PPT, are you able to see?
Yes, sir.
So are you able to see
Yes,
the
sir. You just question mark.
so I've drawn a question mark, green question mark. Okay. Yeah.
Yes, sir.
So yeah, but I don't know why I'm not able to see it on my other screen. So there is I think some lag, but I think yeah it will be there. I think it will come. So then the next step is so once we have assigned the causality for the source effort, so then the next priority would be the inductance and the capacitance elements. So for the inductor, our causality would be at the other at this end, whereas as per the rules for the capacitance element, so the effort variable is calculated on the left side. So for the capacitance elements, our causality will be like this, and then for the next would be basically for the transformer elements. So now we have the one junction. So in case of the one junction, so now we need to have, so in case of the zero junction, so for the now next we will assign basically the causality for the transformer element. So now we have two junctions, like one is zero junction and the one junction. So now as per the rule for zero junction, since we already have one bond with the causality bar at the zero junction, so other two bonds at the zero junction will not have the causality bar on that side. So now for the transformer element, then the causality bar has to be on the left side, so of bond 6, and similarly on the left side for the bond 5. So now we have satisfied the rule for the one junction for the causality. So all the so for the zero junction we have satisfied the rule. Now for one junction, so we have 5 bonds at the one junction. So out of that, bond number 3 has the causality bar on the other side. So now we have to have the rest of the bonds should have the causality bar at the junction itself. So now we can attach the causality bar for the resistance element now, and then our causality assignment is now completed. So basically, as we followed the rule of causality assignment, so first we picked up the causality for the source effort, then we assigned the causality bar for the inductance element, then we assigned the causality bar for the capacitor element, then the transformer element, and then we also uh, have taken into consideration the junction, uh, the rules for causality assignment for the junction, and then after that the last causality assignment was done for the resistance element. So is that okay?
Yes, sir. Okay.
Okay. Yeah, so we have to now to answer this question. Now we have to again draw the causality bars here. So the question is, which are the strong bonds at the one junction and the zero junction? So let us quickly do the causality assignment once again. So yeah, so first we start with the source effort, then the causality bar for the inductor element, which will be this and this, and then for the capacitance element we will assign the causality bar here, here, and now because of the zero junction, our causality bar has to be on this side for the transformer element, and on this side for the transformer element, and lastly we assign the causality bar for the this one.
C, 3 and 7.
Yes, you're right. So it's basically 3 and 7. So bond number 3 will be the strong bond in case of the one junction, and in case of the zero junction, the actually in case of the zero junction, the bond which has the causality bar on the side of the zero junction is considered to be the one. So yeah, it's actually bond number 3 and 8. So
Okay.
so so this particular bond and this particular bond, so that has to be like bond number 8 and bond number 3. So the correct answer is 3 and 8. Now in the next uh, question we have a electric circuit diagram, and now we have to draw its bond graph model. So So are you able to see the slide which has the electric circuit diagram?
Yes, sir.
Yeah, okay.
I am able to see.
Okay, okay, fine. So yeah, so let us start drawing the bond graph for this particular example. So we have a voltage source E over here, and let us say that there is a current I1 flowing through this branch, and let us say some current I2 is flowing through the branch which contains the resistance R2 and the capacitance C2, and then through the inductor let us say current I3 is flowing, and then again the, cur the current I1 will be again flowing here, and then in the current flowing through R3 and C1 will be again split up. So now to draw the bond graph, so we first start with the source. So this is a voltage source, so we have to draw the which component. So source effort will be the component that we will draw first. Then next we have the current is basically flowing through R1. So so we can represent it as a one junction in which current is going to R1, and then here so basically current I1 is being split into I2 plus I3. So now then we will have a zero junction. So for which so one branch will actually go to the inductor L, and now the other part will go to the branch containing the resistance R2 and C2. So the other bond we can represent, so the other branch we can represent it as a one junction. So if, because the current I2 is flowing through both R2 and C2, so now we can represent it as a one junction. And here the R3 and C1, they are both basically subjected to the same, the voltage across both R3 and C1 is same, so then we can represent that branch as a zero junction. So we can draw it as R3 and C1. So the other branch which I was talking about, so we can draw it as R2 and C2. So is that correct? So am I uh, doing the correct thing? Okay. Yeah, so basically what we do is here, so in this case, like in the first loop where the current I1 is flowing, so the what we have is that the effort, sum of the effort here. So let us number this, bond as 1, then this one as 2, 3, 4, 5, 6, 7. So we have numbered, let us say, all the bonds now. So what we have is that the so the effort is now the sum of the, so which is the effort E1. So capital E is actually E1. So which is the sum of E2 plus E3 plus E4. And E4, so E4 is basically the voltage across R3 and C1. So now, and because this is a zero junction, the voltage across R3 and C1 should be equal. So therefore we use the zero junction so to represent this thing. So where E4 is equal to E5 and E6 all are equal, and then the current I1 uh, will basically be split. So now because this is a one junction, uh, so then current I1, so the current flow variable across the bond number 1 and 4 should be equal. And similarly, the current flowing through R1 is also I1. So so therefore then we use the one junction here, and then the next thing is basically we use the zero junction to represent the two branches which contains the inductor L and the R2C2 branches in parallel. So therefore the voltage across these two branches will be the same. So that's why we use the zero junction to represent them. So the bond number 7, it represents, so basically the current I3 will be flowing through this, and then the current I2 will be flowing through this branch. So in case of the one junction, so both the current I2 is flowing through both R2 and C2. So therefore in this one junction, it is the current I2 that is flowing here. Now we can start assigning the causality bars for each of these bonds. So first we will assign the causality for the source effort. So the source effort will be we'll have the causality on the other side. Now next we assign the causality for the inductance and capacitance element. So for the inductance element, so we will draw the bar like this. And for the capacitance, we will draw the bar this way. So now because this we have the zero junction here for bond number 4, 5, 6. So now since bond number 6 has already been assigned the causality bar here, so then we cannot have any more causality bars assigned here. So therefore the causality of R3 should be on this side. Now if we have to assign the causality for this particular bond here in, so which is at the zero junction here, again bond number 4, so the causality has to be this way. Now we come to the zero junction here, so so we first consider the junction number, so junction 1 as yeah, so basically this is how you can assign the causality bars to it, and then further. Now how do we further assign the next causality bars now? So were you able to see the like the red colored annotations which I did for drawing the causality bars here?
No, sir. I am seeing here that electrical component diagram only.
No, earlier. No, I think the okay, that has gone actually. So yeah, yeah. I think anyway we'll go to the next question. No, there is still a problem in my network actually. That thing is not appearing. Whatever I'm doing is not appearing on my screen. So uh, but anyway, right now you are able to see the problem with the like the two masses and the spring damper. All that figure. Are you able to see that on the screen?
Yes, sir. I am able to see that figure where two masses and spring system,
Yeah. Okay. Okay.
spring and damper
Okay.
system.
Okay. Fine. 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 Yeah. So now we have to draw again the bond graph for this system. So yeah, so now we start drawing the bond graph here. So we can see that there are two masses M1 and M2 and there is a spring. They are both connected by a spring K1 and there is a damper R3 connected. And there is friction R1 and R2 acting between the surface mass and the surface. So now how do we start this diagram? So first we have to start with the source. So there is a source effort over here. So because force F is applied, so then we can start with the source effort. So where the effort is F. So and then we next we have the mass M2 and the spring, the damper R3, and then this resistance R2 here. So all of them have a basically the common velocity. So then we can represent all these things by one junction. So we can use one junction to represent these things like so. First, let us draw the bond for resistance R2. And then the other component will be R3. And then we will have to use a capacitive element which has the spring constant K1. And there will be the inertia element M2. I think I should draw this on a new page because there is less space here. Let us start drawing the bond graph again. So we start with the source effort. Then we'll use an inertia element M2. Then the capacitance element for spring K1 and another resistance element R3. Now the other end of K1 and R3, the springs K1 and R3, they are also connected to the mass M1. So now we have to use another one junction now because they will have the common velocity, and and then the component R3 is also connected here on this one junction, and then we will have to draw another bond to represent the friction R1, and then finally the inertia M1 to represent the mass M1. So this is where we can draw the bond graph for the this system. Now we can assign the causality. So for the source effort, we will draw the causality here. Then for the inductor element, we will the inductor element, we will show the causality here. For the capacitance, we show it here. For the inductance, again here we will show here. So for the one junction, we cannot have it here. So the rest of the causality bars we can assign based on the rules for the junction and the um, other resistance and capacitance elements. So now let us move to the next question. Yeah. So now we have been given the bond graph here, and we have to basically derive the equations of motion from this particular bond graph. So now for that, so here the bond graph is already complete with all the causality bars assigned, and so then what we have to first do is to identify what are the system variables. So so to identify the system variables, we have to basically identify which are the inductance and capacitance elements here, and then uh, use the P, like basically identify the P and Q variables, which are basically the integration of the effort, or like for the inductor element. So it's basically the integrated effort, which is the P quantity, and the quantity Q for the capacitance element, which is the integration of the flow variable. So so the system variables we will use basically now, since the bonds have already been numbered, so then we have we have to just identify which will be the so we have to just identify and put what will be the system variables. So the it will be basically, so we have inductor L2, here capacitance C, and then we have another inductance element L1. So the system variables will be basically P2, P5, and Q4. So these will be the three system variables. So where basically P2 is basically the integration of the E2. then P5 is again integration of E5, and Q4 is the integration of the capacitance element. So integration of the flow variable, so it will be integration of F4. So these are the three system variables. Now what we have to do is, so the next step is to identify which are the um, so for the inductance, capacitance, and all the other uh, elements, what are the flow and effort that are being contributed by these. So since P2 is the integration of effort, so the flow that we obtain, so for the bond number 2, so F2, so F2 has to be P2 P2 by L2, sorry. So F2 has to be P2 by L2, and then similarly for the bond number 5, we will get the value of F4, F5. So F5 will be equal to P5 by L1. So these are the flow variables that we get, and then for the capacitance element, so our effort is the outcome of like so the effort E4 will be, so as per the inductance element, so we can write it as Q4 by C. So these are the flow variables and effort variables for these three elements. Now further we have to identify the flow and effort variables for the other, like the resistance components also. So let us look at bond number 3. So for that, so E3 will be R2 F3, and since it is part of the one junction, so it is also equal to R2 F2. And we already know what is the expression for F2. So we have basically calculated E3 in terms of F2. Now next we come to bond number 6. So there we can calculate what is the effort E6. So it is basically R1 into F6. So flow variable 6. So which is now, because it's a one junction, so we can also write it as R1 into F7. Now since bond number 7 is part of the zero junction, then we can write F7 as F8 plus F9. So now I'll have to actually move to our next slide. So E6 as we said is equal to R1 into F7, and which is equal to R1 into F8 plus F9. And since bond numbers 8 and 9, so we say they are like part of the one, like two one junction, so F9 is actually equal to F2, whereas F8 is equal to F5. And we have already calculated the expressions for F2 and F5, so we can calculate basically the expressions for E6 in terms of so our next step will be basically to uh, now relate basically the effort for E2, and then the flow flow for the capacitance element. So basically the system, now we have to find out the state space equation for the system. So for that we'll have to again write down the equations for the uh, like let us say our system variables are P2, Q4 and P5. So then we have to find out the expressions for P2 dot, P5 dot and Q4 dot. So P2 dot is basically the effort E2 and Q4 dot is equal to the F4, and the third thing is basically the P5 dot. So basically we need to get the expressions for P2 dot, Q4 dot, and P5 dot. Now for getting these system equations, like we need to uh, look at the bond graph again. So if we look at the bond graph in the question, so we can see that, so basically effort E2 is part of the one junction, so E2 can be written as E9 minus E3, and since 9, bond number 9 is part of the junction which contains the bonds 7, 8, 9, so we can write it as E7 minus E3. And E3 has, we have already calculated that it is R2 into F2, which is already known. And E7 we can write it as E1 minus E6 because it's part of the one junction. So can write it as E1 minus E6 minus R2 F2, and E6 also we just calculated it here as R1 into F2 plus F5. So E6 is known, R2 F2 is known, E1 is also known because it is the source effort. So we basically got the equation for P2 dot. Now similarly we have to do the same thing for Q4 dot. So Q4 dot is F4, so which is the flow variable here. So it is same as the flow variable because in it's part of the one junction, so therefore flow variable F4 is equal to F5. So and F5 is already known to us, so it is calculated. So we got Q4 dot in terms of F5. And then our next step is to calculate what is E5. So for E5 it is part of the one junction, so we can write it as E8 minus E4. And since 8 is part of the zero junction, so it is, so E8 is equal to E7, so we can write it as E7 minus E4, and E4 is already known to us, which is Q4 by C, and E7 we just calculated as E1 minus E6 minus Q4 by C. So like this, we get all the system equations. So then our next job is to just substitute the known variables and rearrange it in a state space form. So that I think you will be able to do it on your own. So yeah, so it's I think time up for today's session. So I hope you were able to follow at least to some extent whatever. So I also tried to explain and demonstrate some of these problems. Yeah.
Thanks, sir, for
Yeah.
nice session.
Yeah, so basically this topic is a little bit abstract, so it is sometimes like difficult to follow. It has like just lot of procedure, but I think by practice you can I think understand and visualize what is actually happening physically. So I think it will come by practice. So it's like learning a new language altogether. So yeah, so I'll also try to complete whatever problems that I have. Uh, covered today and in the slides, so whatever I'll be uploading, and so I'll be sharing the recording as well as the slides along with them. So
Yes, sir.
yeah, so I think hopefully that should help you in understanding and solving the problems in the assignments. So
Yes,
yeah, so I
sir.
think we can I think end our session for today here. So thank you so much
Yes,
for
sir.
attending, and
Yes, sir.
yeah,
Thank you, sir.
yeah, okay, thank you.